So now let's check out what's happening in section 2.6, combinations of functions and composite functions. So what we'll learn to do is how to add, subtract, multiply, and divide functions. We'll also form some composite functions, and then we'll use the combinations and compositions to model and solve real-life problems. Excuse me. So let's look at the algebra of functions. So if you can add, subtract, multiply, divide, then this will be very easy. Oh gosh, excuse me. The only thing is the notation can be a little tricky. So let's take a look at some definitions. So suppose we're working with two functions, f and g, whatever they happen to be, and they have overlapping domains. Then for all of the x's that are common to both domains, the sum, difference, product, and quotient are defined as follows. If you want to find the sum, or if you're asked to find the sum of two functions, the notation will look like this. All this notation tells you to do is to take the f function and add him to the g function. So when you see this, this is what you're going to do, f of x plus g of x. When you see the notation f minus g of x, that's just telling you to write the f function and subtract from it the g function. This notation, f times g of x, is a notation that tells you to multiply the two functions. Just set them up and multiply them. Finally, this notation right here, f divided by g of x, is just telling you put the f function on the top, put the g function on the bottom, and divide them. When we construct a division out of two functions, we've got to make sure that the denominator is not equal to 0. So when we form the quotient, we have to check that denominator and make sure that make sure that the denominator is not equal to 0. You'll see that in an example. So let's suppose we have two functions. F of x is x minus 5, g of x is x squared minus 1, and let's find the sum, difference, product, quotient, and do some evaluating. All right, since the domain of f, which is x minus 5, is the set of all real numbers, and the domain of g is the set of all real numbers, we have overlapping domains, and they overlap at the set of real numbers. So the domain of the resulting functions when we add, subtract, or multiply is going to be all real numbers. So every one of these operations will have a domain. We could either write all real numbers using that R notation, or we could say negative infinity to positive infinity. All real numbers are negative to positive infinity. Now on the quotient, we've got to be careful because we can't have division by 0, so we're going to save that one for later. But simple operations. F plus g of x tells me to take the f function and add him to the g function. So f is an x minus 5. We're going to add that to the g function, which is x squared minus 1, then combine like terms. So the result would be x squared plus x minus 6. F minus g of x basically says to take the f function and subtract from it the g function. So the x function is x minus 5. We're going to subtract from it the g function, which is x squared minus 1. Now, the most common mistake made on the subtraction is forgetting to put in parentheses. And you must put the g of x function, the second function, in parentheses because of the subtraction. You have got to distribute that subtraction to the polynomial that's behind it. Once that's distributed, we'll just combine like terms. X minus 5 minus x squared plus 1. And when I combine like terms, I get a negative x squared plus x minus 4. That would be the end result. This notation, f times g of x, just says to take the x function, the f function, and multiply them by the g function. So I'll take x minus 5, set him in parentheses, and multiply him by the x squared minus 1. And remember, these are two, this happens to be two binomials, so we'll use the FOIL method to multiply it out. So x times x squared is x cubed. X times a negative 1 is a negative x. Negative 5 times x squared is negative 5x squared. Negative 5 times positive 1 is positive 5. Now let's see if we can combine any like terms and then write this in descending powers. No terms to combine, so I'll have x cubed minus 5x squared minus x plus 5, and that would be our ending result. Last notation is telling us to take the f function and divide it by the g function. So the f function on top would be x minus 5. The g function on the bottom would be x squared minus 1. That basically is your answer. However, we cannot have division by 0, so when I construct a division, I have to exclude any value that makes that denominator 0. So I'm just going to come on the side, set x squared minus 1 equal to 0. Whoops, not equal to 10. Equal to 0. And solve it. And that's a quadratic, so it's going to have two answers. And since it's missing the middle term, I can just take the 1 over and use the square root method of square rooting both sides. When I do that, I have to remember to put in the plus or minus. So if x was equal to plus or minus 1, that would give me division by 0. So what I have to do is say x can't be plus or minus 1. So my domain would be all real numbers such that x can't be plus or minus 1. Or if I use interval notation, in interval notation, it would be negative infinity to negative 1, parenthesis, negative 1 to 1, parentheses on both, and then 1 to infinity to show that the negative 1 and the 1 are excluded. Now let's do some evaluating with these same operations. So this is asking me to evaluate f plus g at x equal 3. So it could also be written like this. F plus g at 3. This just means we're going to go to f and plug in a 3, add that result to the g when we plug in a 3. So f of 3 plus g of 3, well, if I go to the f function and plug in a 3, I'll get 3 minus 5. And if I go to the g function and plug in a 3, I'll have 3 squared minus 1. And all I need to do is now perform that operation. Find the result. So 3 minus 5 is a negative 2 plus 9 minus 1. So we should get 6 as our result. All right, let's evaluate f times g at x when x is equal 0. So we want to basically find f times g of 0, which means find f of 0 and multiply that times g of 0. So we're going to go to f, plug in a 0, and we get 0 minus 5. Then we're going to multiply that result by going to g and plug in a 0. That'd be 0 squared minus 1. So I end up with a negative 5 times a negative 1, which gives me a positive 5 as my result. Last one, let's evaluate f minus g at x when x is equal negative 2. So this is f minus g of negative 2, which means go to f and plug in a negative 2, subtract from it a g when we plug in a negative 2. Let's do it. F of negative 2 means I'm going to have negative 2 minus 5. Then I'm going to subtract from that g at negative 2. So if I go to g and plug in a negative 2, I'll have negative 2 squared plus, not plus 1. There is a minus 1 behind that. So let's find those two values and multiply them out. So negative 2 minus, let's find those two values and subtract them. So negative 2 minus 5 will be a negative 7 minus negative 2 squared would be 4 minus 1, which would be 3. So I get negative 7 minus 3, which would be a negative 10. Let's pick up with a little work on the domain. So let's review that concept. I've got the function f of x, a new function, which is the square root of x minus 3, and a g of x, which is the square root of x plus 1. I want to find the domain of I want to find f divided by g of x and state its domain. So let's first look at the domain of the functions individually. Remember, when you have a square root function, you've got to take that radicand, in this case x minus 3, and set it greater than or equal to 0. The radicand in this case is x plus 1, and set it greater than or equal to 0. Because remember, you can't square root negative numbers. They end up being non-real values. They end up being complex numbers. We'll work with those a little later on. So if I set x minus 3 greater than or equal to 0 and solve that for x, I get x greater than or equal to 3. And if I solve x plus 1 greater than or equal to 0 for x, I get x is greater than or equal to negative 1. So there's the domain of those guys individually. Let's set up f divided by g of x. That means I'm going to take the f function, put it on the top, g function, put them on the bottom. So that means I'm going to have the square root of x minus 3 over the square root of x plus 1. So there is f divided by g. But the domain of f divided by g is the intersection of the two domains listed above. Where would those two domains intersect? I'm going to draw two number lines. X greater than or equal to 3 would be everything from 3 to the right. And x greater than or equal to negative 1 would be, whoa, I didn't want that to happen. Okay. X greater than or equal to negative 1 would be everything to the right of negative 1. Did it again. All right. So now where would these two domains overlap or intersect? Where would the red shaded portions overlap? And it would be here, x greater than or equal to 3. So the domain of f divided by g is the intersection of these two, which would be x greater than or equal to 3. However, since we created a division, we also need to realize that I can't have division by 0. Well, the only number that would make this denominator be equal to 0 if x was equal to negative 1. Well, notice that negative 1 is not in this overlapping domain, So actually, it's not a concern for this particular problem. So the domain of f divided by g is this overlapping domain x greater than or equal to 3. Or we could write that in interval notation as a bracket on the 3 to the infinity. I'll stop it here and then we'll pick up with composite functions.